we continue, and I'm going to switch gears a bit in the beginning. So up till now, I think all of the examples that I covered and that we discussed involve triangles in the complete graph, trying to decompose the complete graph into triangle-free graphs, trying to find the largest subgraph of the complete graph or the random graph that doesn't have triangles, or we're talking about typical structure or structural graphs which are triangle-free and close to the maximal one, the structure of typical triangle-free graphs, and so on. And some of these questions we addressed using the container theorem for triangle-free graphs. First in the weak version, then in the strong version. But until now, I have not said a single word about how to prove such a container theorem for triangle-free graphs. So what I will start with today is stating a more general theorem, which will imply this container theorem for triangle-free graphs. And this is the hypergraph container theorem. And I'll use it to discuss, so I'll discuss the statement of the theorem and the assumption, and we'll derive the container theorem for triangle-free graph from this general statement. And I'll give you, in the remainder of the course, which is today and tomorrow, I'll give you two more examples of this, which are still somewhat simple to state, and they both have a kind of a bit different flavor than the examples that we've discussed so far. So yeah, without further ado, let me state the theorem. So let me say that in the end of the teens, sorry, the 2000s, there was a lot of interest in the types of theorems that I was discussing, namely these extremal theorems in random settings, like the random version of Mantel's theorem. Even though it was proved by Frankel and Rull in the 80s, there were generalizations of it that were still open. And there were two very important works due to David Conlon and Timothy Gowers, and another work due to Matthias Schacht, and also a work on Ramsey problems due to Ehud Friedmuth, Wojciech Samotij, and Matthias Schacht. And kind of, there were really great works and resolved many open, conjectures. And kind of one very important insight here was that there was a collection of questions that people thought of separately, and they had the idea of saying, they're actually kind of different facets of the same more general problem. And this proved to be kind of extremely useful, and also kind of motivated our work on the hypergraph container theorem. So here's the framework that was put forward in these works. And the framework is to state all these theorems concerning, say, triangles in the complete graph, or arithmetic progressions among the integers 1 to n, or kind of copies of K4 and so on. In the complete graph is the language of hypergraphs. So the setting is that H will be a K uniform hypergraph, which is nothing else than certain collection of K element subsets of some finite set. So then once you have a hypergraph, you can speak about independent sets in such a hypergraph, which are just subsets of vertices of the hypergraph which don't contain any of its edges or hyperedges. So the hypergraph, you can simply think of it as some collection of K element subsets of some finite set V. And now the independent sets in such a hypergraph, which I will denote by I of H. These are all the subsets of this vertex set of the hypergraph, with the property that I does not contain A whenever A is an edge of this hypergraph, so a set from our specified collection. And using this abstract language, you can actually express many objects that we're studying in combinatorics. In particular, the entire discussion about triangle free subgraphs of the complete graph can be expressed in this abstract sense in the following way. So what are triangle free subgraphs? They are in fact independent sets in the following hypergraph. I can let the vertices of the hypergraph to be the edges of the complete graph. And the edges of this hypergraph will be triples of vertices, which is triples of edges of the complete graph that together form a triangle. So these are the collections of all UV, UW, and VW, such that U, V, and W are vertices of the complete graph. So the first time you see it, it's a bit confusing because the edges are the vertices, and then the hyper edges are collections of edges. So I will try to say hyper vertices maybe in the beginning and hyper edges, because edges are hyper vertices and triangles are the hyper edges. So kind of edges are just not triples of vertices of the triangle, but rather the triples of edges of the triangle. And what is an independent set in here? It's a collection of hyper vertices, which means collections of edges, which you can think of as subgraphs, so that no set of this form is contained in this subgraph, which means the subgraph doesn't contain three edges U, V, U, W, VW, meaning the subgraph is triangle free. So here I of H is in one-to-one correspondence with triangle free subgraphs of the complete graph on n vertices. Triangle free subgraph of Kn. And in fact, there's nothing special here about the triangle. If I wanted to speak about, say, subgraphs of Kn, which don't have a cycle of length phi, then we would define a phi uniform hypergraph where the vertices would still be the same, and these hyper edges would be just edge sets of all the phi cycles that you can see in the complete graph on n vertices. So why is it useful? Well, it's useful because, in fact, instead of proving a container type theorem for each graph separately, one can prove a container theorem for independent sets in hypergraphs under some kind of abstract conditions, and then just apply it to these various cases of interest by just verifying some assumptions on the hypergraph. And what do these assumptions involve? So it turns out that the existence of a family of containing sets or independent sets and in the hypergraph depends on very simple statistic of the hypergraph. Just the number of edges, the number of vertices, and the sequence of degrees of the hypergraph. And the sequence of degrees I will define here because we will not speak only about degrees of hypervertices, but also degrees of pairs of hypervertices, triples of hypervertices, and so on. And let me define it formally for every subset T of the set of vertices. We may define the degree of T in this hypergraph H. This will be the number of edges of the hypergraph which contain this given set A. And whenever we're given a number L between 1 and K, we will let delta sub L of H to be the maximum value. So the maximum possible degree of a set whose size is exactly L. So this generalizes the notion of maximum degree, say in graphs. The maximum degree is simply delta 1. So it's the largest over all. So if L is equal 1, we go over all the vertices of the hypergraph. The hypervertices will look at the number of edges that contain this given vertex. So it's the usual notion of the degree. So let's give an example. If Hn is the hypergraph of triangles, what is its number of hypervertices? So we said that hypervertices are the edge to the complete graph. So it's simply n choose 2. Now, what is the number of hyper edges? Hyper edges correspond to the triangles in the complete graph. So this is simply n choose 3. Now, what is the maximum degree here? The maximum degree would be the largest number of edges, so the largest number of triangles that contain a given hypervertex, which means a given edge of the complete graph. But in fact, every edge of the complete graph is contained in precisely n-2 triangles, because you just need to choose the third vertex. So this is equal to n-2. How about the maximum 2 degree? So a pair of edges in the complete graph, how many triangles is it contained in simultaneously? If these edges don't share endpoints, then it's 0. And if these edges do share an endpoint, then it's precisely 1. It's the edge determined by the non-overlapping endpoint. So this is 1. And of course, any 3 edges of this hypergraph, so sorry, 3 vertices of this hypergraph, meaning 3 edges of the complete graph, either they form a triangle or not, but some triples do, so this delta 3 is equal to 1. And with this definition in place, I can now state the general container theorem for independent sets in hypergraphs. And this theorem was proved by Yoshi Balog, Rob Morris, and myself, and independently by David Saxton and Andrew Thomason in 2015. And here's what it states. Whenever we take an integer k at least 1 and parameters k and epsilon, think k large, epsilon small, there will be a constant C positive such that the following points. Suppose that H is a K uniform hypergraph that satisfies the following condition. For every L between 1 and k, this maximum L degree is at most some number b divided by the number of vertices to the power L minus 1 times the ratio of edges to the vertices, and here I put a constant k for some integer b, which is a parameter. So this, the larger the b, the easier it is to satisfy the condition. Then there is a family S, which comprises of independent sets of size at most c times this parameter b, and functions G. Every independent set is assigned, is labeled by some element of S, and F, which to every element of S assigns some subset of the vertices in such a way that one, for every independent set, the value of G of I is some subset of I, and I itself is contained in F of this subset. And the second condition for every S, F of S induces very few, it's almost an independent set. So the number of edges in the hypergraph that are induced by this set F of S is at most an epsilon proportion of everything. So I use the same notation as for triangle free graphs. So the meanings of the functions G and F and this family F are exactly analogous. So let's try to read it. We assume something about the hypergraph. We bound its degree in terms of this parameter B, which we are free to choose. So the larger the parameter, the easier it is to satisfy it. However, we will look for this, the smaller b, the smaller this family S is, so we get a stronger statement. And the conclusion is that we are able to label every independent set in the hypergraph by its subset of a relatively small size in such a way that to every label we're also able to find a subset which is almost independent in the sense that it induces only an epsilon proportion of all the edges of the hypergraph, so that this independent set is sandwiched between its label and this almost independent set that depends only on the label. So in particular, in the weak version, if we forgot about this condition, we're able to find a family of subsets, each of which is almost independent, that cover all the independent sets. And the size, so note that the size of S is its most exponential in the log of the number of vertices. So for triangle free graphs, this B was N2 3, so with H is corresponds to triangle free graphs. So now you see why I didn't start the lecture series like this, because I think out of no listeners 20 minutes into the course. But since we're already somewhat familiar with the statement in this particular case of triangle free graphs where things are more explicit, I hope this is not too overwhelming. But maybe let me stop here and ask if you have any questions about the statement. And my next step would be to derive the container theorem for triangle-free graphs from this abstract statement, just to see how to use it in a case where we already know that this container theorem for triangle-free graphs might be useful for some things.
So it's slightly different with the container theorem for triangles. Right? So in a container theorem for triangles, this S should not be, it is not necessarily an independent set, right?
Well, a posteriori it is. So I didn't write it this way, but since we said that every graph gets labeled by its subgraph, and since we're labeling only triangle-free graphs, then the labels themselves have to be triangle-free graphs as well. But thanks, John. Yeah, this is a good comment. So we could have added this condition before, but we never used it in the arguments explicitly. Okay, so let's try to use it, and let's derive this container theorem for triangle-free graphs that we discussed yesterday and 2 days ago, and from this statement, just for an illustration of how to use it. And it will kind of come in handy that we've already calculated all the parameters of the hypergraph in question, because these parameters will determine what is the smallest value of P that we can plug into this theorem. So the question is, what is the smallest P that we can use in the theorem for the case H is triangles in Kn. And let me stress again that the only way that B appears in the conclusion is here to bound the size of this labeling set. And of course, the smaller the B, the stronger the statement, because we get a smaller family of containers. So it's in our interest to take B as small as possible, but this limits how small the B is, because all these inequalities have to be satisfied. So since the uniformity K is equal to 3, there are precisely 3 conditions that we need to verify for L equals 1, 2, and 3. So when L is equal to 1, then we're asking for delta 1 of H to be at most K times is, sorry, the number of edges divided by the number of vertices. However, we know that the number of edges is n choose 3, and the number of vertices is n choose 2. And we also calculated this to be exactly n minus 2. And the right-hand side is precisely k times n minus 2 over 3. So this suggests that maybe we just take k equals 3. So this inequality holds with equality. Now, L equals 2. We ask the maximum 2 degree, which is equal to 1, to be at most now 3 times b over the number of vertices times the number of edges divided by the number of vertices. And for L equals 3, we ask 1, which is the maximum 3 degree, to be at most 3 times b over vh squared times the number of edges divided by the number of vertices. Note that this is a stronger requirement because taking b to be just, so this ratio b over v of h is of course at most 1. If we take b to be the number of vertices, then the statement there is trivial because we can just label every independent set with itself and we don't get anything useful. So this inequality will imply this inequality because b will be much smaller than the number of vertices. And so this I will write as 3 times b divided by n choose 2 squared times n choose 3 divided by n choose 2. So as you see, this gives a lower bound on b. Now we know that 3 times that is exactly n minus 2. And therefore, this is equivalent to requiring that b is at least 1 over n minus 2 under square root times n choose 2. I just multiplied by n minus 2, took square roots of both sides, and multiplied again by n choose 2. So, therefore, we can easily take b to be n to 3 halves. So, we need roughly b to be roughly n to 3 halves, maybe n to 3 halves over 2, but it's, I mean, this factor of 2, since we're only dealing with asymptotic statements, doesn't make any difference. And we still have this constant c there, which anyway will depend on the epsilon that we will choose in the case. So since we can use b being n to 3 over 2, then we recover the statement of the container theorem for triangles. So we just apply this to this hypergraph. We check that b equals n to 3 halves is sufficient, and we take k to be 3, large k to be 3, and b n to 3 halves, and we get a family of containers for triangle 3 graphs, where the labeling sets are graphs with at most c, which depends on epsilon, times n to 3 halves edges, which is precisely what I stated yesterday or 2 days ago. Do you have questions about that? So I will give you now an exercise. And the exercise will be to find the best family of containers for H-free graphs, not necessarily only triangle-free graphs. Find the smallest family of containers for H-free graphs. Meaning the family of all subgraphs of Kn that don't contain a copy now of some graph H, and the more explicitly, the important parameter here is the so-called two density of H, which is the maximum value of the ratio of the number of edges minus 1 divided by the number of vertices minus 2, where J ranges over all subgraphs of H with at least 2 edges. And show that the assumptions are satisfied when B is value n to the power 2 minus 1 over the two density of H. And just for a sanity check, what is the two density, of the triangle? Well, the triangle has only two subgraphs to check. The path of length 2, which has 2 edges and 3 vertices, so it gives 1 over 1. But it's also the triangle itself, which is 3 minus 1 divided by 3 minus 2. So it's precisely 2. And then you see that we're asked to show that the assumptions hold with B equals n to the power 2 minus 1 over 1/2, which is 3/2, which is precisely what we've done. But now there's many more conditions to check. However, I already told you what the answer should be, so you don't need to guess the B, but just to verify that indeed this is satisfied. And the second part of the exercise, which is the main part, will be to reprove all the theorems that we proved about triangle-free graphs for H-free graphs. So reprove all the theorems about kind of Turan and Ramsey properties of the random graph GNP under the assumption P is goes to 0 slower than n to the power -1 over the two density of H. So, in analogy, what we've done so far, instead of proving Mantel's theorem, its version for H-free graphs, and then prove that under this assumption, any RH coloring of GNP has a copy of H in one of the colors. And you could also try to prove the example about typical structure of the largest H-free subgraph of GNP. For the typical structure, you will need to assume that the graph H is not bipartite, because if the graph H is bipartite, we don't know that such statements hold even when P is equal to 1, even for the complete graph. And maybe this would be a good time for a break, unless you have some questions. Maybe let's kind of try. I was intending to discuss the optimality of the assumptions here, but maybe instead of doing it abstractly, let me do it on the example of these questions about H-free subgraphs of random graphs. So I want to argue that these assumptions, at least if you write them in this form using the maximum degree, cannot be further improved. So that they up to the choice of this constant C, kind of this is the best you can hope for. And the argument would go as follows. Suppose that you can verify the assumptions of the theorem for this hypergraph of copies of H in the complete graph. Let's forget that we prove this, and let's just say that someone promised us that we can prove it for some abstract value of B, but we don't know how it relates to the graph. Now, then you could prove the same theorems using the assumption that P tends to 0 slower than B over n squared. So this is kind of the only assumption we need on P. Here to push through all these arguments that P tends to 0 slower than B over n squared. I mean, it checks with the triangles, because for triangles we assume that P goes to 0 slower than 1 over root n, and B just happened to be n to 3/2. But after you will solve the exercise, you will see that this is the only assumption that we need. Because kind of we need to kill the union bound over all the containers, and our probability estimates are exponentially small in Pn squared, whereas the size of the union bound is roughly exponential in B. So as soon as Pn squared is much larger than B, then the probability estimate will kill the union bound, and we'll be able to push through these arguments. So this is kind of hand waving, but this is essentially what is happening here. Now, why do we need to assume that B is at least related to this 2 density? So let's recall, how did we argue for optimality of the assumptions in the case of triangles? We said, suppose we assume something opposite, and then we'll show that actually G and P contains a much larger triangle-free subgraph than we would expect by comparison with the complete graph. So how did the argument go? And we said, so optimality of assumptions. Note that if you were interested in lower bounding this function, there are 2 ways we could do it. We could say this graph would contain roughly the same proportion. So take some largest H-free subgraph of Kn. We can intersect it with G and P, and typically we keep the same proportion of edges roughly as we would keep as we have in the complete graph. And we want to prove that this is optimal. But we could also argue as follows, in this more silly way, that we keep all the edges. However, from every copy of H that we see in G and P, we remove arbitrarily 1 edge without keeping any structure. So minus the number of copies of H in G and P. Now, in expectation, this is n choose 2p. And this is at most n to the number of vertices of the graph H times p to the number of edges of the graph H. Now, if this is much smaller than that, then we would get, say, 99% of, maybe, sorry, 99% is not good anymore because the graph is not bipartite. We're competing against 1 minus 1 over the chromatic number of H. So let me say that this would be just essentially everything if the expected number of copies of H is much smaller than the expected number of edges. So it's the same assumption as for the case of the triangle, just there, this was 3, this was 3, and we replace it by, so n to the VH is the number of copies roughly of H in the complete graph, and it has EH edges, so in the random graph, this is the probability that each such copy survives. And this is equivalent to saying that P is less than n to minus the power VH minus 2 divided by EH minus 1. And what is this? It's minus 1 over EH minus 1 divided by VH minus 2. Great. So where does this maximum come from? Maybe it would be enough to just assume EH minus 1 divided by VH minus 2. Well, the maximum comes from the following kind of rather silly observation. Let's fix some subgraph J of H. Instead of removing one edge from every copy of H, I could remove one edge from every copy of J. Well, since J is a subgraph of H, if I removed all the copies of J, I would also remove all the copies of H. So we can replace all the H's with J's. So now we need to assume that P is at least a constant times this for every J. And therefore, this leads to the notion of the two density. So maybe kind of surprisingly, sometimes it's better to run this argument for some subgraph rather than for the entire graph itself. And the example is, suppose we're looking at cliques of size 4, where we add, say, a long path. Now, the minute a clique appears in a random graph G and P, then already the average degree is pretty high. So for every clique, we see many ways to extend it to this graph. So if we said, let's remove one edge from every copy of that, then we would just be removing these edges from the paths all over the place. Whereas the best thing to do is to say, let's just remove one edge from every clique. And this is much more efficient because with one edge, we kill many such subgraphs. And this is essentially the reason why it's not enough to assume something just about the last degree, but we need to assume something about all the degrees simultaneously, because this, so for example, here we have 6 edges here and 3 here, so it's 9 edges, but somehow the bottleneck comes from considering the degrees of this, because every such 6 edges can extend to many such paths. This causes delta 6 in this hypergraph to be pretty large. So I have prepared some abstract argument, but maybe kind of arguing by examples would be of more value and more convincing than arguing abstract. Do you have any questions about this example?
Why do we need to remove one edge from every copy of J? I mean, maybe we remove one edge and we will destroy more than one copy of J.
Yes, you are right. Of course, it could be that there are more efficient ways to do it. The only thing I'm arguing here is that even if we consider this silly looking lower bound for the Turan number by blindly removing one edge from every copy of J, not in an optimal way, still this shows that we need to assume something about the density of the graph, because otherwise we'll get a bound on this extremal function, which is much better than what we would expect just by analogy with the Erdős-Stone theorem.
So it's not the best way, but
So it's not the best way, but in low densities, it's better than just considering some large partite subgraph, because there aren't enough copies. So the copies of H aren't sufficiently uniformly spread so that it would enforce the best construction to be like in the complete graph. Okay, so in the remainder of today, my plan is to prove another theorem, which I was unable to state in the case of triangles. So it's also kind of, I showed you several applications of the container theorem for triangles, and now I'm kind of happy that we only talked about triangles because there are things that are more explicit, and the hypergraph is explicit, the bounds are explicit. However, the problem that I'm going to address now doesn't make any sense in the case of triangles, because it degenerates to a different problem, which we actually have already solved. And this problem is the notion of induced Ramsey numbers. So all of you, before you came here, you knew Ramsey's theorem, and I'm not sure if all of you know the induced Ramsey theorem. So who here has heard of the induced Ramsey theorem? And who here has heard of it but is too shy to raise their hand? Okay. So Ramsey's theorem says we color a large enough complete graph, then you will see a monochromatic copy of a clique on a given number of vertices. And therefore, you will also see a copy of every graph, because fix my graph H, I can just look for the complete graph on the same number of vertices. And once I see this complete graph, I will also see a monochromatic copy of any graph on the same number of vertices. Now, the induced Ramsey question asks us for something stronger. I want to find, so I'm given a graph H, which is not complete. And I'm asking, does there exist a large graph so that no matter how I two-color its edges, I will find a monochromatic copy of H that is moreover induced in the large graph. So set of vertices where the induced graph is H and all the edges are either red or blue. All right. G. Induced Ramsey for H in our colors if every R coloring of the edges of G has an induced copy of H in G whose all edges are monochromatic. So all edges are of the same color. Well, the reason why it doesn't make sense for triangles is that any copy of the triangle is an induced copy of the triangle. But as soon as H is not a complete graph, this is no longer the case. And it's not even clear whether such a graph exists. So it doesn't follow from Ramsey's theorem. And so Ramsey's theorem was proved in the 20s. And the fact that for every H and R you can find such a graph was proved only in the 70s by Neuber, Erdős, Einar, and Posha, and by Riddle. So this is in the 1970s. So they proved that for all H and R, there is a graph P, which is induced Ramsey for H in R colors. And they gave some explicit constructions, which for which these graphs were really, really enormous. And there was some interest in getting bounds on G in terms of H and R. So for usual Ramsey numbers, the bounds are exponential in the number of vertices of H. Well, for general H, and if H is sparse, then you can get much better bounds. And what I wanted to show you as another application of the theorem is a proof of the existence of such G, which gives reasonable values for the number of vertices in such a graph. And if you think about it, it's very natural to think that the random graph will have this property for the following reason. If there is a graph which has this property and this gentleman proved that such a graph exists, then any graph will appear as an induced subgraph of the random graph Gn1/2 when n is exponential in the number of vertices of this graph. And therefore, if such a graph exists, then at some point we'll find it in the random graph Gn1/2, maybe by exponentiating the number of vertices. So it's natural, if you want to prove the existence, to consider G to be the random graph Gn1/2, but of course, maybe it's not entirely clear how to argue that Gn1/2 will have this property once n is sufficiently large. And I'll show you how to use this theorem to make such an argument. Okay, are there questions about the statement? So to do this, let's analyze what it means for G to not have the property. So suppose that G does not have this property. So what does it mean? It means that we can find a coloring of the edges of G that has no induced copies of H in any of the colors. So let phi be a bad coloring. And now we may think of phi as being a coloring of the complete graph, where we additionally use the color 0 to color all the edges of the complete graph which are not in G. So we may think of phi as a coloring of the complete graph on this. So n will be the number of vertices in G, with the colors now 0, 1 up to R, where we color the edges not in G by 0. And now, what does it mean for phi to be bad? Here's what it means for phi to be bad. So we're looking for H, which has VH vertices. Now, whenever we consider some subset of VH vertices in this large colored complete graph, it must not be true that there's an embedding of H there whose all edges have color I and whose all non-edges have color 0. This is precisely what it means that there will be an induced copy of H in I. There's some embedding of the vertex set of H into the large graph. All its edges are colored 1. Sorry, all its edges are colored I for some I, and all of its non-edges are colored 0. Because 0 means it's not an edge of G, which means that this copy was an induced copy of H in G. So in symbols, this means for every H, which is an injection of the set of vertices of H into the set of vertices of the complete graph, and for every I, it is not true that if we look at the edges of H colored I and the non-edges of H in color 0, this must not be the coloring of I, of the edges in this set. So I think here of phi as its graph. So for every edge in the complete graph, I have some color between 0 and R. So these are the edges. These are the colors from 0 to R, and I can just graph the coloring. So over every edge, I just put 1 point in Kn, and this way the coloring is just a subset of the Cartesian product of the edges versus colors. So I'm looking for a color I. Now, the edges of some copy of H would get color I, the non-edges would get the color 0. This would correspond to an induced copy, but we don't have such an induced copy. And this is precisely the condition.
Patients with this frame, each of H, you map vertices.
So I map vertices to vertices. So now H of H, so this induces also a map on the edges, because if I take a pair of vertices, both vertices are mapped to some vertices of the complete graph. So the pair of vertices mapped to a pair of vertices of the complete graph.
Yeah, it's just that on the first one, it needs pairs. But here, each of H is rather, what does each of
H of H, sorry, this means it's the set of of pairs HU, HV, whenever UV is an edge of H. So I take all the, so it's the image of a set of pairs through this function, which is lifted from a function that sends vertices to vertices. So this is a collection of edges of a copy of H in the complete graph, and this is the set of edges of the complete graph, which is the complement of this copy of H on its set of vertices in Kn. So here, this is a two-colored copy of the complete graph on V of H vertices in Kn. So if this has E of H edges, then this has VH choose 2 minus EH edges. So we colored all the pairs in some subset of VH vertices inside Kn. In other words, we found a clique in Kn on VH vertices, and its edges are now colored in two colors, in the color I and in the color 0, so that the color I forms an H and the color 0 is its complement.
Oh, there is a one question from John. Is this length number?
So the induced Ramsey number will be the smallest number of vertices in such a graph G. So you may ask, why did I make all of this more complicated? So we started with something which was clear to everyone, and I expressed it in a way that was confusing for everyone. And the reason is that writing things in this form allows me to be in the context of the theorem. Because what is this condition? You can think of phi as some subset of this Cartesian product. And this subset has the property that it doesn't contain any subset of this form. So if now we define a hypergraph on this set of vertices, whose edges are all sets of this form for all functions little h and all I, then this is just a hypergraph of uniformity VH choose 2, because each of these sets has precisely VH choose 2 points. And therefore, this phi will correspond to an independent set in this hypergraph. So in particular, if G with the coloring phi is not induced Ramsey, for H in our colors, then this phi, when viewed as a subset of this Cartesian product, is an independent set in the hypergraph on this set of pairs, edge and color, whose edges are all the edges of the form, the images of edges of H times some color I, plus the images of the non-edges of H times the color 0 over all possible embeddings H, and all colors between 1 and R. So these are all the restrictions. We look at all possible ways to find a copy of H in Kn. We color this copy I, we color its complement by 0, so this would give an induced copy, which is also monochromatic on the edges. And we don't want any such induced copy to be present in our coloring phi, because this would mean that the graph is in fact Ramsey. Sorry, that this coloring is in fact Ramsey.
I think the definition of the function h, maybe we can use the VH to n to 2, maybe. And then in this way, if you use the hypergraph, if it is k uniform, so the function of h maybe VH to k to, I think maybe it's clear. Yeah, because the little h and the capital H, yeah, actually you have the k elements in it.
So you said that
Yeah, I mean the function of
the little a.
Yeah, I think maybe you can use the VH to K. Maybe it's clear if it's K uniform, something like that.
It will
So
go.
it's not a VH to VKN.
It is VH to VKN because we're mapping the vertices. I just need to also make sure that this function is injected. I'm just mapping the vertices of H into Kn, and this will give me a labeled embedding of the vertices of H into Kn. And then I will know where to put all the edges.
Yeah, I know.
Now, continue. So we have this hypergraph, and I would like to apply the container lemma to this hypergraph. But we need to find this parameter V, and the exercise is that this hypergraph satisfies the assumptions of the theorem with B being n to the power 2 minus 1 over the 2 density of which graph? Not of the graph H, but of the complete graph on V of H vertices, because in fact, these things are kind of copies of the complete graph on VH vertices, not copies of H. They're just two colored.
And the implicit constant depends on R.
The implicit constant will depend on R. So this is also another important remark here is that even though every coloring corresponds to an independent set, of course, not every independent set corresponds to a coloring, because an independent set would say not color an edge, or it would give an edge 7 different colors. But since we want to rule out bad colorings, it's enough to rule out certain independent sets. So this is only kind of a representation going one way, unlike in the previous cases. But here it's sufficient for our purposes. So one other thing that we have to learn is, what do we learn from the fact that something is a container, that it's sparse? And so suppose that we have a set B, which is a subset of the vertices that has fewer than epsilon proportion of all the edges of the hypergraph. And how many edges are there in this hypergraph? Well, the order of magnitude is given by the number of possible ways to find this injection from VH to V of Kn, and we also have the choice of colors, and that's about it. So this is theta of n to the V of H. Also, for different injections, which give us the same subset of vertices, but in a different order, maybe these two things would be the same, but up to a constant that depends on H, this is n to NR, this is n to the to V of H. So theta of epsilon n to VH. Edges. So given such, I want to argue that this implies that certain large proportion of edges of the complete graph, they don't have a color available other than perhaps the color 0. And to argue, let's define a coloring psi of the edges of the complete graph with colors 0, 1, up to R as follows. The color of an HE, if for this edge, both the colors 0 and I are available in V, then I would like to color it I. So it's will be the maximum of all I such that E0 and EI are available for V. And if I don't have a color I, where 0 and I are available for E, I will color it 0. So this is some coloring of the edges of Kn. Now, we proved something when we're talking about Ramsey theorem for triangles. We proved that any coloring of the edges of Kn with color 0, 1 up to R either has some epsilon n cubed triangles in some color, or epsilon n squared edges in the color 0. So either at least epsilon n to the V of H copies of the clique on VH vertices in some I in R, or at least epsilon n squared edges color 0. The same proof will give us the statement, with the only distinction that before in the proof we used the Ramsey theorem for triangle, now we will use the Ramsey theorem for VH, and we get a different constant epsilon. Let's rule out the first case. Suppose that we have, so this is this large complete graph with the coloring psi, and suppose here we have a clique on VH vertices whose all edges are colored I. This means that, however, I choose here a copy of H inside this clip, the color I is available for it, but also the color 0 is available for its complement. Meaning that this way I get an edge in H using only what's available for me in B. Again, if we define this coloring, finding a clique with color I means that on all these edges, both the color 0 and the color I are available. So I can just, regardless of how I make this split, I can find H in color I and complement of H in color 0, just because both colors are available. So this is regardless of what H is. So if there's so many of these copies, then this would give me many, many edges in the hypergraph induced by B, but we assumed that the set B induces very few edges. So this is in contradiction to the fact that B is a sparse set. Contradicting the fact that B of HT is less than epsilon and 2. Now, it must mean that this holds for a quadratic number of pairs. But what does it mean that we colored some edge of the complete graph 0? Either the color 0 wasn't available for this edge, or it was available for this edge, but then we couldn't find even a single I which was available for this edge. So this means that for all such edges, B does not allow E0 or does not allow EI for any I. Okay, now we're really at the end. Let's consider now the event that Gn1/2 is not Ramsey. What's the probability that Gn1/2 is not induced Ramsey for H in our colors? This is the probability that Gn1/2 has some bad coloring phi. But we built a family of independent sets for these bad colorings. So a family of containers for these bad colorings, because every bad coloring is an independent set. So this is at most the sum over all B, which are containers, the probability that Gn1/2 has a bad coloring phi, which is contained in this containing set B. The number of containers, so the size of the sum, is at most exponential in n to the power 2 minus 1 over the 2 density of the clique on V8 vertices times log n. But the only important thing is this is strictly less than 2. What does it mean that GN1 has a bad coloring phi, which is contained in B? Well, for every such B, we have this bad set of n squared edges where we do not allow this color to be 0, or we do not allow any color other than 0. If we do not allow the color 0, we color 0 everything that is in the complement of GN1 . So if we do not allow 0, it means that this edge must be an edge in GN1 . If we do not allow any color I, it means we cannot color this edge in any color, which means that this edge cannot be in GN1 because if it appeared, we would have to color it. So this probability is at most 1/2 to the power epsilon n squared. Because these are the edges where E0 is not in B, then E must be in GN1 . Or EI not in B for all I. This means that it must not be in GN1 . Because if it was, we wouldn't be able to color it. And if it wasn't, then we have to color it 0, but we cannot because B tells us that we cannot do it. And now, so we have something exponential in n to 2 minus c for some c that depends only on the number of vertices times 2 to the power minus epsilon n squared. And this is of course small because this exponential is smaller than n squared. This is exponential in n to 1.999. And yeah, that completes the argument, and I really apologize for going over time.